Good afternoon, everyone. I am Ahsan from University of South Carolina. I will present my work on platinum functionalized graphene silicon Schottky diode based hydrogen sensor. First, let's take a look what I will cover in my talk. First, I will talk about the hydrogen sensor applications, then the recent research trend in the semiconductor based hydrogen sensor. Then I will introduce the concept of graphene silicon Schottky diode. I will call it as Chemi diode. Then the sensing response of functionalized graphene, this Chemi diode. I will compare the graphene Chemi resistor and graphene silicon Chemi diode, the response between these two. Finally, I will present the sensing performance and tunability, and I will wrap up my talk in my conclusion slide. So, the hydrogen sensor application, hydrogen is used in different industries, and it is also important in some other in places. The thing is that hydrogen is hazardous, odorless, and highly flammable above 4 volume% in air due to its really low flash point. Hydrogen sensors are used in combustion gas detection in different types of transportation. Then it is a source of clean and renewable energy as a in the form of fuel cell, and it has hydrogen sensors finds lots of application in different type of different industries. Now, if we take a look in the recent trend in semiconductor based hydrogen sensor, mostly platinum or palladium, they are forming Schottky contact with the conventional semiconductors, or platinum or palladium is coated on top of these devices to make them hydrogen sensitive. And apart from this, some other sensors, for example, this nanomechanical or photonic crystal vertical cavity laser, these are coated with either platinum or palladium to make them hydrogen sensitive. In recent years, this carbon based material, they attracted lots of research attention. Initially started with carbon nanotube, and then in last few years, graphene, both epitaxial and CVD graphene, and then chemically synthesized multilayer graphene nanoribbon network, all of them is either coated with platinum or palladium. They are sensitive to hydrogen. Now, here I am focusing on the unique properties of graphene that we are going to apply in our device to make it more sensitive. First of all, zero band gap and semi-metallic nature with a large work function which can make a Schottky contact with other semiconductor, conventional semiconductor. Then the second important aspect is tunable work function. We can tune the work function by electrical, optical, or chemical means. And finally, interface state-free junction is possible between chemically inert graphene and other semiconductor. So this is the band diagram of our device. We started with P-type graphene, whose band gap is whose work function is in the range of 4.5 electron volt, and we took P silicon, which has a work function in the range of 5. So there is sufficiently large difference in work function to form a Schottky contact, whose characteristics is governed by this harmonic emission model. And in reverse bias, the reverse current is exponentially proportional to the barrier height at the interface, which is slightly different from the conventional graphene Chemi resistor sensor, where when graphene is exposed to molecules, the carrier changes and current changes almost linearly. So you will get a linear change, but here we are expecting exponential change. Now here is the growth and device fabrication steps. My colleague in next talk, he will focus more on growth. So I am just going over the steps. First, we started growing graphene on copper, and then this graphene on copper still patterned by optical lithography and patterned in strips by RI. Then in parallel, we did optical lithography on silicon dioxide silicon substrate and removed silicon dioxide from selectively by HF etching. Then Ti-gold contact pad was deposited on top of silicon selectively and annealed to make ohmic contact. Then this patterned graphene is transferred on top of this silicon dioxide silicon substrate, and in those places where silicon is open, graphene made contact with the silicon, and that formed Schottky contact. Then this titanium gold contact pad was deposited on graphene on top of SiO2, and finally we functionalized this device by depositing platinum very thin. Um, Next, if we take a look, this is the optical image. This side, this is showing graphene on top of silicon dioxide with platinum coating, so it is showing some contrast. This side is silicon, it is not showing any contrast. And we took a SEM image of this, and it is showing these are platinum grains due to the very small growth duration. They could not form a continuous film, so these are 20 to 30 nanometer grains. And we then did the Raman characterization to see the graphene quality. Left side, this is as grown graphene showing good quality and single layer. But when we transferred on top of silicon and then functionalized it, its D by G ratio which characterized the quality, it increased slightly from 0.3 to 0.54. This is due to probably the point defect formation at the time of platinum deposition, and you can see also the silicon peak is also visible. When we did the electrical characterization of this diode before platinum deposition, the characteristics is dominated by rectifying this thermodynamic emission model and the typical rectifying characteristics with ideality factor of 1.68 and Schottky barrier height of 0.64 electron volt. Ideality factor, this is slightly greater than 1 due to the barrier height inhomogeneity at different places, plus the image force induced barrier lowering. Then we did the electrical characterization at different stages after platinum deposition and after hydrogen exposure. What happened is initially it was 0.64 electron volt the Schottky barrier height, which decreased to 0.59 with platinum deposition. This happened due to this platinum, they doped the graphene more, the p-type doping, and then its work function increased, but the barrier height, overall barrier height, that decreased, so it is decreasing from 0.64 to 0.59. With hydrogen exposure, this again increased to 0.62. This is due to the platinum hydride formation which induced dipole, and that decreases the work function of graphene and ultimately increasing the barrier height of this diode. And if we check if we check the response at 4 volt forward bias in terms of current change, it is 5.5%, and in reverse bias it is 69%. In forward bias we are not getting really high response. This is due to the series resistance domination over the exponential change. So in this diode, when only series resistance is changing, it is changing linearly, but in reverse bias the current is really small, and there the current changes exponential with the change in barrier height. So that exponential nature dominates, and that's why we choose this reverse bias operation for this diode in our next studies. To directly compare the performance of graphene silicon chemidiode sensor and the graphene chemiresistor, we fabricated these two types of device on the same sample side by side with the same transferred graphene and functionalized with the same amount of platinum. What we found is 106% change in resistance for chemidiode compared to only 7% change for chemiresistor, which is showing 15-fold improvement in sensitivity. Another important fact is lower power operation of this chemidiode. Since this is operating in reverse bias in microamps range, the so overall power of operation is microwatt, and compared to the milliwatt for chemiresistor. In this slide, I'm showing the result for of the sensitivity variation for different hydrogen concentration variation. So we varied the hydrogen concentration from 10 ppm to 1000 ppm, and sensitivity varied from 5.5 to 103%. Same time, the response and recovery, with the increase in hydrogen concentration, the response and recovery time, they decreased. It is expected. Other people also found these types of behavior. The another important fact I already mentioned, graphene's work function, which is completely different from other metals, you can say. It is semi-metallic, so its work function we can tune by electrical, optical, or chemical means. We applied that concept here. We varied graphene's work function with different applied bias. So when we applied different bias, say from -1 volt to -5 volt, its sensitivity increased from 27.5 to 77.5%. It is shown here, plotted different bias. With the increase in bias, it is increasing. And to substantiate that, we measured the same device again at higher bias at -8 volt. And for example, I am taking 10 ppm. At -4 volt, it is showing 5.5% change, and at -8 volt, it is showing 13% change. And with that high applied bias, we detected down to 1 ppm. So here I am summarizing my findings. We demonstrated the platinum functionalized graphene silicon Schottky diode hydrogen sensor, which showed at least an order of magnitude high sensitivity compared to the graphene chem resistor. And then we demonstrated hydrogen down to 1 ppm. Hydrogen sensitivity, we can tune that by the applied reverse bias. And these devices, we can operate this in really low power, in microwatt range, compared to the milliwatt range for conventional graphene chem resistor. So thank you all for your attention. I am acknowledging for our source of funding to National Science Foundation. So thanks.